In fact, let's go to this picture first, and then we'll go to the numbers. So here's a series of photographs where you adjust the amount of light coming into the image from 1,000th of a second to 1/4 of a second. You see here, there's an outdoor part of the scene right there, so 1,000th of a second is enough. Actually, when you open it up a little bit more, it gets a little bit easier to see these things. And then as I let in enough light that I can see the interior really well, this outdoor thing is totally blown out. And yet, if you were to stand there, what you would see is something that looks like this. You'd have no problem seeing the indoor stuff and the outdoor stuff. It might be, a little bit harder to see, but not anything like the camera. And that's because your system deals with dynamic range so much more effectively. Okay? Here's another example of photographing a high dynamic range scene, right? So if you wanted to see the stained glass really well, you'd have to miss the rest of the inside of the church. If you want to see the rest of the inside of the church, these things get blown out. But you would have no problem seeing this. You would see the beautiful stained glass, and you would see the church. You now know that there are computational photography methods called high dynamic range. So you have a high dynamic range on your iPhone or your little phone or whatever, or in Photoshop, something like that. That's a way of blending together a series of pictures to automatically select which regions from which image should be selected, or how much you dial up or dial down each region of the image in order to composite the whole thing into a high dynamic range image. Putting some numbers behind this, the dynamic range that the human eye can deal with is incredible. It ranges over 14 orders of magnitude. And there's almost nothing in the real world that works over 14 orders of magnitude, right? So that means 10 to the 14, 1 and 14 zeros times from the darkest dark to the brightest bright that you can deal with. And by the way, that does not include looking like directly at the sun, because frankly, you can't actually see much when you look directly at the sun. It's too bright, all right? But you can go from somewhere from 10 to the -6th to 10 to the 8th, what's called candelas, which is a unit of energy, per square meter. It's a measure of the amount of the flux of the light, and flux falls on a particular area. So the human eye can set its dynamic range, its set point, to anywhere from this really low, this 10 to the -6, 10 to the -5, 10 to the -4, so that'd be a range of 2, up to 10 to 6, 10 to 7, 10, another range of 2. It can set it anywhere along that spectrum. At any given point in time, it's operating at least 100 to 1, maybe 1,000 to 1, maybe even more than that, depends upon how you're doing. And in any given sort of real-world scene, like I was just showing you, the actual ratio of sort of the darkest area to the brightest area can sometimes be on the order of 100,000 to 1, right? So you're standing there, it's really bright outside, it's kind of dark in here, that difference might be 100. If it was that far, even your eye would have difficulty dealing with it. But it's way better than most imaging systems. Now the thing is, everybody knows about your pupil, right? When it's bright out, the pupil closes down. When it's light, when it's dark, the pupil opens up. That's a very small range of variation. A colleague of mine, the professor, actually used to say that it was like an order of 10 to 100 variation in terms of the size. He actually said 10, but I think it's a little smaller than that. But how do you do this great, huge variation? Well, it's actually the retina's ganglion cells that make this happen. And the way it does it is, and this is sort of looking at just a single section. So remember, light's coming in this way. Not too important for this thing. Here we have our photoreceptors. Here we have our horizontal cells, our bipolar cells, amacrine, and then there's these ganglion cells. But notice that this thing is referred to as the surround, the center, and the surround. And you can think of this as being a slice through a circular operator, okay? And that circular operator would look something like this, okay? In the retina, they're referred to as center surround receptive fields. And what that means is that, and the positive ones takes the illumination that's from the middle, and they subtract off the illumination around the background. The negative ones do the negative in the middle and subtract and add the positive. But basically what they're doing is they're comparing the local illumination to a little patch of illumination to the overall illumination. So what happens when things get much brighter? Well, if it's just getting brighter over the whole thing, not a lot different changes. So one part of your retina can be sort of electrically and chemically setting its dynamic range at one place, and another part is at another place simultaneously. So the part that's looking at the bright window in the church is operating at one place. The part that's looking at the darker part It's doing its center surround on a darker area, but it's looking at those relative contrasts. This plot here is just a notion of what a center surround field looks like. Now, one of the cool things is you can actually measure the center surroundedness of a ganglion cell while it's working, okay? I wouldn't recommend doing this to you or to anybody else you have any care for whatsoever. But basically, the way you do recordings is here's a schematic of a neuron. So it has dendrites where they receive inputs from the synapses. And when the inputs are correct, it will generate a spike of firing down here. And then these terminals impact the next nerves that it's in contact with. And if you were to put an electrode right over here, you would occasionally see these spikes. And neural coding we tend to refer to as the more spikes per second is a higher level. So we've gone essentially from analog to digital, right? In an analog system, the amount of the voltage tells you how high it is or how low it is. In a digital system, there's something discrete that tells us, okay, there's 15 ones and 2 zeros, that's a higher number than all zeros, or et cetera. Well, in the neural system, the way we do is we look at how often is the neuron firing. And you can actually go ahead and do this. This is a picture of a micropipette, an electrode, getting ready to record from a neuron. So you do these with neurons that are still living, right? This is why I said you wouldn't want to do this to anybody you cared for, right? And what you can do is you can then put different kinds of stimuli at different locations in the eye and see what happens, all right? And if you do that, you can find areas. So here we have, when it's just black, this neuron doesn't do things very much, okay? But when it's white in the middle, okay, and black out here, all right? And what this is, oh, by the way, this is time going this way. So this is when the spot was turned on. You can see when it goes from the background, this is called the background activity. When it goes from the background, when it turns on, this thing starts firing crazy, and then you turn it off and it stops again. Okay, fine. But what's then cool is if I then turn on a really bright spot, okay, nothing happens. It stays just like my background. And in fact, if I want to turn the cell off even more, I turn on just the outside and I make the middle black. And here what you can see is it actually just shut down the background altogether. And then when I turn the thing off, it wakes back up again and then returns back to its normal. So this is an on cell, okay, that is, its center is positive. Exact opposite cell here is negative, okay? And both are found in the retina. The other thing that's found in the retina are ganglion cells whose size in terms of their response is different. So there are ones for very small, for medium, and larger. And your system is actually tuned to have more of a particular size, and that tuning is what gives you this phenomena. So again, this is going to be a function of how your monitor is calibrated, all right? But the contrast sensitivity function, so for me, so what this is this is a sinusoid where the frequency goes up this way, and contrast goes up as you get further down, all right? And the question is, where can you see the bars? And for me, I can see the bars kind of like that, okay? So the question is, why can't I see this stuff here, but I can see this stuff there for the same level of contrast? The answer is my retina has more and a better tuned receptors at this size frequency than at this size frequency. This phenomenon that you're seeing is a function of what goes on inside your eyeball. And that can be graphed out looking like this. Two things interesting about this graph. First is this is a function of frequency, and here they use different luminance levels. So they make it brighter and it's sort of how sensitive you are. And then something, and for the PETA folks amongst you, please ignore this, you'll notice that the human data and the macaque is a type of monkey, are very, very similar. Now this is done, of course, without doing anything to anybody, right? You just ask them, what do you see, etc. But what this data show is that the vision system, the retinal vision system of the macaque monkey is really quite similar to the human. So if you were to do experiments on primates measuring physiological things, remember those electrodes, we have reason to believe that what we learned there is the same would apply also to the human system. So when you have psychophysical experiments like this, it shows you the similarity between human and macaque. So at the retina, this local contrast information is being measured. It's being selectively done on different colors, and that's going to go out the optic nerve and then start getting its way into the rest of the brain, starting with the lateral geniculate, and then further processing takes place up in the cortex, and both of those will be the discussion for the next lesson. All right, welcome back to Computer Vision. Today we're going to finish our little tour of the visual system of the human visual system, the anatomy of the human system. So when we last checked in with our heroes, we had this little model going on here. Remember, here's our nose over here. Here's your eye, and it's got the optic nerve going through this optic chiasm, and it goes to this first area called the lateral geniculate. And then from the lateral geniculate, most of the stuff goes to the visual cortex, although some goes to superior colliculus, which we'll also talk about. Last time also, we discussed in some nauseating detail what goes on in the retina. So today is going to be sort of what goes beyond, from above the retina. This little section here, this little lateral geniculate, is actually part of the thalamus. If you were to take that thalamus and take a slice of it, which is what they're showing here, and then you stained for cell bodies, and the neuroanatomists, they really have all sorts of clever ways of applying different kinds of chemicals that light up in different colors or intensities, the different types of cellular structures that are there, so you can actually see what's going on. If you took this slice, you would see that the lateral geniculate has got these layers, right? You can see this layer 1 right here, right, and layer 2. And it's really remarkable that they have these fixed layers, right? Because remember, these things just grow. It's not like somebody got there with a soldering iron and built them. These things grow to have these computational structures, right? So if you take, the double E's or computer scientists among you, you're used to seeing schematic charts of high-end chips that have all these layered structures in them. You've got your transistor arrays here and different memory things there. These things just grow like this. Pretty cool. And the layers are different. In fact, you can actually tell a little bit that layers 1 and 2 seem to be a little bit different than layers 3, 4, 5, and 6. And in fact, they are. Layers 1 or 2 are called the magnocellular layers, and these are referred to as the parvocellular layers. And the most important difference for you is that 1 and 2 tend to be the where cells, and these are referred to as the what cells. And that has to do with where they project going forward. We'll talk about that in a minute. The other thing to know is that both eyes project to the left side for whatever's looking at the right half side of the visual field, and both eyes project to the right side from what's looking at the left-hand side of the visual field. Well, you can see that explicitly in the lateral geniculate. Layers 1, 4, and 6 come from the same side eye, and layers 2, 3, and 5, did I get that right? Yep, come from the other side of the eye. So we haven't combined the two eyes yet, right? We still have two separate channels. Why do we have to combine the two eyes? Well, how about things like stereo? Well, that's going to go on up in the cortex, right? You have to be able to get both of the images together. But at the LGN level, lateral geniculate, they are still separate. The where goes up to the superior colliculus, which you can see on this kind of creepy picture here. So here it is, kind of creepy, right? You got your eyeball. Anyway, what you're seeing here is this coming in optic chiasm through the lateral geniculate and then projecting up to the superior colliculus. And the thing that matters, as I said, I think earlier, the superior colliculus is involved in eye movements. So one of the things that has to happen very quickly is if something moves over here, I have to be able to get my eyes over there very, very fast. All right? So you have very good sensitivity to motion in your retina in the periphery, and then you've got a circuitry that's involved in rapidly going, it doesn't make many neural stops along the way, right? We go from your retina, which is doing some chemical stuff sort of right away, one electrical stop into the lateral geniculate and directly to the superior colliculus. Now, as I said earlier, this is an overly simplified story. I encourage you to take a course on sensation, perception, and neuroanatomy if you're interested in this, but the story is pretty close. So anyway, those layers 1 and 2 go directly to the superior colliculus. But where's the really cool stuff happening? Well, the really cool stuff happening is when you leave the lateral geniculate and you get up to the cortex. So here is another picture of your brain just to remind you of where pieces are. Again, your nose is over here. Here's your cerebellum.